Hi, this is a presentation on how the Bayes multinomial classifier can be used for signal processing applications. The classifier has been used for text processing for some time and spam filtering as well. The classifier takes an n-dimensional input data set that's been previously associated with a given outcome and then makes predictions given future sets of n-dimensional data that hopefully are able to predict future outcomes. It's called naive because it simply examines the conditional probability of each individual event in the n-dimensional data set without necessarily investigating higher order combinations. It's appropriate for use in categorical data, which is why it's called the multinomial classifier. And one application of using this might be in determining who you're going to solicit for donations. You could examine historical trends in donations, for instance, by categorizing people who donated before by their profession, whether or not they have money, and whether they're past people in distance to the school. And then using that data set, you could train a classifier to determine what kind of decisions you're going to make in the future as to whether you're not going to solicit those people for donations or not. So here's the signal processing application we're going to take a look at. We're going to assume that we've got a customer who's got a manufacturing system, and they're making a high-speed transmission system that can produce 10-bit test patterns. Test patterns are produced by sampling this waveform at intervals of 100 nanoseconds. But there's some process problems that can cause a failure in that signal. The manufacturing staff has noticed that certain patterns are associated with certain process problems. For example, some patterns are more common when the clock is early, and some are more common when the clock is late. You can see if there was an edge right here where you expect to get a 1, if the clock came a little bit early, you would get a 0 there. Similar here, where you would expect to get a 0, you would expect to get a 1. So here's the sample program running in Visual Studio with the source code available on the GitHub. The first thing we're going to do is generate a nominal case. So in this case, we've shown the waveform up here that we've sampled. And this is the output waveform after the flop. So as we expect in the nominal case, where we're assuming no clock skew, we get the same value every time. We've sampled 100 times. And that's shown here. Now we're going to go over here, and in this case we're going to generate 100 instances of a late arriving clock and 100 instances of an early arriving clock. We're going to assume this is a stochastic pattern, so for each case a negative or positive random number is generated with a standard deviation of 50 picoseconds, and that's applied to the respective clock edge. When we do this, we can see that certain patterns are occurring more often in the early case. Mainly this pattern, for instance, occurs very frequently, but then some other patterns occur more frequently as well. Similarly, in the late case, we have a clear dominance here of this pattern showing up. So we can see just based on this histogram that at least for the late case there might be some way to infer some behavior. Now we're going to train the Bayes classifier, and that's going to allow us to use historical information to predict future events. Now that we've trained it, we can do a first pass to determine how good the classifier is by feeding back the training data. And that's what we've done here. This is called an error matrix. Essentially all we've done is resubmit our training data back into the classifier. So it shouldn't be too surprising that we should be able to at least be able to get something back from that's similar to what we had classified. It's just a sanity check. So in this case we can see the in our error matrix we've got all the nominal cases are correctly identified as nominal. The late cases did a pretty good job of identifying those as well. So 93 of the 100 late cases were properly identified. The early cases, not so good. And you can see that here in the histogram that we're seeing here, that the late case does not happen or the early case is not trained quite as well. It's not quite as obvious. Now when we click Test Bayes, we're going to generate a new set of random data, and we're going to apply the Bayes classifier to that. So again, we can see we've got good correlation for the nominal. So for all the cases where we actually generated a nominal waveform, or we created a nominal system, the Bayes classifier correctly identified as nominal. And again, we see pretty good prediction of the late case. Early case, not so good. So if we were going to put this into production, we'd probably want to take a look at these test patterns, because ostensibly this should be a symmetric system. So possibly by using different test patterns here or improving on the test patterns, we'd be able to improve this middle case here. The strength of, although you could do something like this just by looking at it or by inspection, the strength of a learning algorithm like this is that the algorithm is able to perform the learning on its own based on a new pattern without necessarily having a person intervene.